You said there's been a teleportation. We've teleported. It's been a prediction of quantum theory for decades, and we've done it with small particles, single particles. So the question is, can you do it with bigger things? You can have 64 qubits. You can instantaneously solve a problem that is exponential because you can explore all of those at the same time. Then, when you measure, scientists at the University of Oxford just pulled off something that could change the future of technology forever. They've teleported data between two quantum computer chips, something that was once thought impossible. Why is this such a big deal? Imagine a computer that can solve problems in seconds that would take today's best supercomputers billions of years. That's the power of quantum computing, and this breakthrough brings us much closer to making it a reality. It also means ultra-secure communication, where messages are protected by the laws of physics themselves, making hacking virtually impossible. This isn't just a small step forward, it's a massive leap toward computers that could revolutionize everything, from medicine to artificial intelligence, changing the world in ways we can barely imagine. Before we start, don't forget to like and subscribe for more latest news on space, tech, and science. Now, let's go quantum. Quantum teleportation. What it is and how it works. Quantum teleportation doesn't involve physically moving objects like in science fiction. Instead, it enables the instantaneous transfer of information from one place to another using a phenomenon known as quantum entanglement. When two quantum particles become entangled, their states remain linked no matter how far apart they are. A change in one particle's state instantly affects the other, as if they were still connected, an idea that Einstein famously called spooky action at a distance. Oxford's groundbreaking achievement, teleporting logical quantum gates. What makes Oxford's achievement truly remarkable is that they didn't just teleport a single quantum state. They successfully teleported logical quantum gates, which are the fundamental building blocks of quantum algorithms. In classical computing, logic gates perform operations on bits, binary values of zeros and ones that store and process information. In quantum computing, these operations are executed on qubits, which can exist in multiple states at once due to a property called superposition. Previously, quantum teleportation had been used to transfer quantum states between separate systems. However, the Oxford team took this further by using teleportation to create interactions between these distant systems. By carefully controlling these interactions, they managed to perform logical quantum operations between qubits located in separate quantum processors. Essentially, they linked distinct quantum processors into a single, fully connected system without requiring any direct physical connection. This addresses scalability in quantum computing. Addressing scalability in quantum computing. This breakthrough directly tackles one of the biggest challenges in quantum computing: scalability. Traditional quantum computers struggle with adding more qubits to a single processor due to increased error rates and decoherence, where quantum information is lost due to environmental noise. The Oxford team's method offers a modular solution. Instead of cramming everything into one massive processor, multiple smaller quantum processors can now be linked together via teleportation. This paves the way for much larger and more powerful quantum computers without the limitations of a single chip. Even more impressive, their experiment demonstrated that this teleportation-based approach is feasible using today's technology. This suggests that practical, large-scale quantum computing may not be as far off as previously thought. Quantum Internet and cybersecurity revolution. The implications of this achievement are profound. First, it addresses the scalability issue, a significant roadblock in quantum computing. Most quantum processors today are small and fragile, struggling to maintain coherence as more qubits are added. By using quantum teleportation to link separate processors, researchers can now build large-scale quantum systems without relying on a single monolithic chip. This distributed approach could form the foundation of future quantum supercomputers. Another major implication is the potential for a quantum internet. Today's internet relies on classical communication methods secured by encryption, which can be cracked given enough computational power. A quantum internet, however, would be fundamentally unhackable, as it depends on the principles of quantum mechanics rather than mathematical encryption. Because quantum teleportation allows for instantaneous information transfer without it physically passing through a medium, eavesdropping would be impossible. This could revolutionize cybersecurity, benefiting governments, financial institutions, and individuals with an unprecedented level of secure communication, transforming industries and advancing real-world applications. Beyond cybersecurity, This breakthrough has the potential to transform multiple industries. In pharmaceuticals, quantum computers could simulate complex molecules, significantly accelerating drug discovery and medical research. In finance, they could optimize risk analysis and trading strategies with unparalleled precision. In artificial intelligence, quantum computing could enhance machine learning models, making them more advanced and efficient. And in climate science, quantum simulations could provide deeper insights into climate patterns and aid in the development of new materials to combat environmental challenges. Perhaps most importantly, Oxford's discovery moves us closer to practical quantum computing, where quantum algorithms can outperform classical computers in real-world applications. While quantum supremacy, the point at which a quantum computer surpasses the best classical supercomputers, has been demonstrated in specific cases, this development brings us closer to real-world usability, where quantum machines will tackle problems classical computers simply cannot. Challenges and obstacles in quantum computing's path. Despite its groundbreaking nature, challenges remain. One of the biggest hurdles is maintaining quantum coherence. Qubits are highly sensitive and can lose their quantum state due to external disturbances. To build large-scale quantum computers, researchers must refine error correction techniques and develop more stable qubits. Another challenge is scaling this method beyond a handful of processors. The Oxford experiment successfully linked a limited number of quantum processors using teleportation, but for a fully functional quantum network, this technique must be extended to global distances. Scientists will need to enhance the technology to ensure it functions reliably across vast networks. The global quantum race, competition and collaboration. Encouragingly, Oxford's work is part of a broader effort in quantum research. Other teams worldwide are making significant progress in quantum teleportation and networking. Engineers at Northwestern University recently demonstrated quantum teleportation over existing fiber optic internet cables, showing that a quantum internet could be built atop current infrastructure, an essential step in bringing quantum networking into the real world. Meanwhile, Google is advancing quantum hardware with its 105-qubit Willow processor, capable of performing computations that would take classical supercomputers millions of years. In China, researchers have successfully teleported quantum states between satellites and Earth, laying the groundwork for a global quantum communication network. Comparing quantum technologies, superconducting qubits, trapped ions, and more. Quantum computing is rapidly evolving with multiple competing approaches vying to become the dominant architecture. The recent breakthrough by the University of Oxford, teleporting logical quantum gates between separate processors, adds a new dimension to this competition. But how does this method compare to other quantum computing technologies, such as superconducting qubits, trapped ions, and topological qubits? Each of these approaches has its strengths and weaknesses, shaping the future of large-scale quantum computing. Superconducting qubits, progress and challenges. One of the most well-known approaches is superconducting qubits, used by companies like Google and IBM. These qubits are made from superconducting circuits that operate at extremely low temperatures, close to absolute zero. Superconducting qubits have demonstrated significant progress in recent years, with Google's Sycamore processor achieving quantum supremacy in 2019 by performing a computation in minutes that would take classical supercomputers thousands of years. IBM has also been steadily increasing the number of qubits in its quantum processors, recently unveiling the 1,121-qubit Condor processor. However, superconducting qubits face challenges with scalability. As more qubits are added, the system becomes more prone to noise and decoherence, making error correction a major hurdle. Oxford's teleportation-based approach offers a potential solution by enabling modular quantum computing, where multiple smaller processors can be linked instead of relying on one massive chip. Trapped ion quantum computing, stability and scalability. Another promising method is trapped ion quantum computing, pursued by companies such as IonQ and Honeywell. This approach uses individual ions suspended in electromagnetic fields, with quantum operations performed using lasers. Trapped ions have an advantage over superconducting qubits in terms of stability and coherence time. Qubits in trapped ion systems can maintain their quantum state for much longer than superconducting qubits, making them ideal for executing long quantum algorithms with fewer errors. However, scaling up trapped ion systems is a challenge since they require precise laser control and complex ion trapping mechanisms. Oxford's breakthrough provides an alternative path forward, allowing multiple quantum processors to interact without direct physical connections, potentially complementing trapped ion systems in building large-scale quantum networks. Topological qubits, a new frontier. Microsoft is developing topological qubits, a fundamentally different approach based on exotic particles called Majorana fermions. Topological qubits are designed to be more robust against errors by encoding quantum information in a way that makes it less susceptible to environmental noise. While this approach is theoretically promising, topological qubits have yet to be demonstrated at a practical scale, making them one of the more experimental quantum computing strategies. If successful, they could revolutionize quantum computing by significantly reducing error rates and improving scalability. However, until topological qubits are experimentally validated, Oxford's teleportation breakthrough presents a more immediate and practical path toward linking quantum systems. A bright future for quantum computing. Ultimately, Oxford's method could complement any of these approaches by enabling distributed quantum computing. Instead of relying on a single monolithic quantum processor, multiple smaller quantum processors, whether superconducting, trapped ion, or topological, could be linked via teleportation to form a scalable, modular quantum system. This could be a key step toward overcoming the scalability challenges that have long hindered practical quantum computing. If you found this discussion exciting, don't forget to like, share, and subscribe for more updates on cutting-edge technology and groundbreaking discoveries. Stay curious, and see you in the next one.